Hello, everybody. I'm Randii Wessen, and what I want to do today is show you a glimpse of tomorrow. Now, these technologies that we're going to be doing are not approved mission concepts. They're not even proposals. These are capabilities that we're trying to do tomorrow to bring your instruments to other places. Let's see. Okay, first, just to put this in perspective, this is a camera looking down on a Delta II, and this is what it takes to leave the Earth. This is not sped up, this is not animated, this is not faked. This is what it takes to leave the Earth, and it illustrates a point of how difficult it is to leave the Earth and how expensive it is. You know, without correcting for real year dollars, a Saturn V was about $1 million per pound. Shuttle was about $100,000 per pound. Today's Delta IV and Atlas Vs are about $10,000 per pound. Elon Musk is doing $5,000 per pound, and he wants to get to $100 per pound. But the first trick is actually leaving the Earth, because you can't afford to do redundant subsystems because you're adding more mass to the launch vehicle, and you have to work the first time, because if you have $1 billion spacecraft and it's non-nominal, you have an issue there. But what I want to show you is when we get to the upper left-hand corner and it's black, it means you're up. So just to show you how long it takes to leave the Earth, we're going to lose the solid rocket boosters. Those are these things here on the side. They fizz out and we just drop them off. And then there they go. And then in the upper left-hand corner, we go black. And we're just about up there. Come on, you can do it. You can do it. And all right, that's how long it takes to leave the Earth. Doesn't take long, but it's expensive, and you want to bring that cost down. Next. Okay, so now when it comes to doing exploration, we want to have different ways of seeing. Next. This is a Mount Sharp. It's white balance, so it means we basically change the coloring as if you were on Earth. If you're a rover and you're driving around and I see these dunes, how do I know if there's a cliff on one side or possibly a femur sticking out the other side? Because I want to go visit the femur. I don't want to go over the cliff. So one of the technologies we're working on next is to build a 2-kilogram helicopter that you can use for helicopter exploration in other worlds. Now, it's not approved to go to Mars yet, but right now we're looking with Mars conditions. I want to show you this thing. Next. This is a video of an actual flight test in our environmental chamber. So we took our 25-foot environmental chamber, we sucked out all the atmosphere, and then we backfilled it to 7/1000ths of an atmosphere to see if we could actually generate lift with this baby 2-kilogram double prop vehicle. So it's got 2 props, 2,800 RPMs in 7/1000ths of an atmosphere. So we fire it up. We put a chain on it to make sure it doesn't hit the walls of the tank. But we demonstrated that we can actually generate lift with a helicopter in a Mars environment. So, you know, now you can argue that you can look up, see what's going around, and then drop down again. And if you think about it, with Sojourner on Pathfinder, having that kind of mobility system was so strong, it led to Spirit, Opportunity, Curiosity 2020. Could this technology lead to future missions that are helicopter missions? Next. Better ways to move. Next. When in 2004 we had the Constellation program, you had the Altair lander, you had the habitat module on top, but nobody had figured out how to get that thing off. So one of the techniques they were working on for a different way of moving was called Athlete. Athlete is all-terrain, hex-limbed extraterrestrial explorer. This exists. This, right now, it's got 6 legs, 6 hip joints, 6 knees, 6 ankles, and wheels. Now, right now, it's kind of like a baby where you have to command each wheel and joint to do things. This is sped up. This takes about 2 hours to do this thing. But now you can drive along, and if you get stuck, you can start walking or you can climb over things. Here you can see it taking a mock habitat pallet off of an Altair lander. This is half scale. But this is just another way of doing mobility systems to try to move things around worlds. So if you think about it, if you just land on a body with humans, that's colonization. If you can actually do movement across the body. Now you're doing exploration, and you can get countries from around the world to help you by caches of supplies that you can just drive to. Next. When we go out to ocean worlds, and again, this is not for Europa mission, but we're just using that as an example. You've got Europa with the ice field. Next slide. We don't know how thick the ice field is. It could be meters, kilometers, tens of kilometers. We think you have hydrothermal vents on the bottom that are keeping the wet stuff wet. If you were going to explore these oceans, we think the most interesting place to explore is not along the bottom, not even swimming in the seas, but we think going right along the bottom of the ice-water interface, because you have convection cells bringing things up from the bottom to the ice interface, and radiation is hitting stuff on the surface that's falling in. So now the question is, how do you do underwater exploration at that interface? Well, we started trying to build something for that. Next. We went up to Alaska with this instrument called Bruy. We pull out an ice plug. National Geographic was kind enough to work with us. That's the yellow square in the upper right-hand corner. That's baby Bruy. We dump it into the ice lake. National Geographic dumped a camera down to look up at this hole, and then we just set it off. It's buoyant, so it floats up, and now it drives under the bottom of the ice field. Now, you know, if you're doing this at Europa, you still have to figure out how to get 500 million miles out there. You still got to figure out how to go through kilometers of ice. You still have to figure out how to get power and commands to it. You still have to figure out how to get data out of it. But we're working on that mobility capability. We're actually even able to control back to our operators at JPL versus just the operators up in Alaska. Next. And then finally, finding new Earths. Next. I don't have to tell you guys about the whole variety of exoplanets that we're finding out there, whether they're hot Jupiters really in close. Next. Orphan worlds, worlds that get kicked out of that solar system and are just coasting through interstellar space. And there's just these worlds out there. Or we've thought about maybe you've got ocean worlds where it looks like the whole surface is just covered with water. The problem that you run into is that the light level between the star that you're looking at and the light reflected off of the exoplanet is about 10 billion to 1. We say it's like trying to see a firefly an inch away from a lighthouse at night when they're a mile away, and then because of zodiacal dust in both places, do this on a foggy day. Okay, foggy night. So that's what we're trying to do. So one of the ideas we like are coronagraphs, but when you put that occultation disk over the target body, you still get diffraction around the edge of it blowing. I mean, you need 10 billion to 1. So one of the ideas that we're working on, and we actually are building some hardware to show you this, I'm going to show you the animation of it. This is called starshade. Next. So there's a telescope. This is starshade. It has the first deployment, then the second deployment. These petals are 2 meters long, and they have micron tolerances. This could be 10, 20, 30 meters across, and then you send it downrange 10, 20, 30,000 kilometers out. And it's a ratio between the size and how far you're going. But you move it in front of the star as seen from the telescope so that you can visibly see planets going around other worlds. This is called the starshade, and we're building this today. It's a bit of a challenge to figure out how to do it, but we're doing it. Next. Why do we do this exploration? The first is because we're curious. It's to explore our universe. When we study other worlds, we can then bring back that information to Earth to better understand the Earth, and then finally improving our lives, because these technologies actually migrate to our everyday lives. So when you think of your cameras in your phones or wherever else, that was a technology that developed an Active Pixel Center at JPL. I want to end with a set of 3 images that I just love. The left is the Earth as seen from orbit. The middle picture is the Earth as seen from the moon. The one on the right, that's from the surface of Mars. Next. And that circle, I don't know if you could see it in this lighting condition, there's a dot there. That's the Earth as seen from Mars. Next. This is Saturn, high phase angle. Next. That's the Earth from 1 billion miles away. I want to end with a quote by one of my heroes, Konstantin Edvardovich Tsiolkovsky. The Earth is the cradle of the mind, but one cannot live in the cradle forever. Thank you. I get a question?